Okay, well, welcome back. The very first thing I'm going to talk about is undoing the contrast transfer function, because as you can see, it's a pretty awful function with lots of zeros in it, and how we're going to compensate for that is a trick. Okay, so this is the simulation of, let me just move this a little bit. This is a simulation that I just showed you of how you get the image using the CTF. You multiply the Fourier transform of the object by the CTF and you get this thing, and if you inverse transform, then you have the actual image. And this is how you simulate, or how you conceptually form an image in the electron microscope. Now let's consider the contrast transfer function operating on a particle. So here's my particle in an appropriate size box. Here's the Fourier transform of the image of a particle. There's the contrast transfer function, and this is a 1D slice of the CTF. So you multiply these two, and you get the Fourier transform of the image, and then that's the image that you get in the microscope. Yeah. So it's typically constant for an image, for one movie or one micrograph that you take. Okay. If the specimen is tilted, though, then it becomes non-trivial, because then the defocus is going to be different in one part of the specimen than the other. So especially the people who do tomography have to worry about the gradient, the defocus gradient in the specimen. But if we're not tilting, to first approximation, the defocus is everywhere the same in a given micrograph. People who work at very high resolution actually do a defocus estimation per particle in case the specimen is not completely flat. But that's something you do when you want high resolution. Let's say, you're going to 2, 1.5, 1 extra.
So per box, you have different CTF per box.
Yeah. Yeah. It gets more and more complicated the higher resolution you want. Okay, so this is what happens to a particle image. And so we can say that the image that we get is the original object, which I'm going to call A, multiplied by the CTF, C, and it has noise added to it. So this is my model for what an image looks like. Now, the question is, can we do this deconvolution? This would be really cool, because we know that all we have to do is multiply these two to get the effect of the CTF on the object. So we could just divide by the CTF, and then we would do a perfect deconvolution. But of course, this is not going to work. Your computer will immediately give you some errors, because you will be dividing by 0 when you have zeros of the CTF. So how are you going to do this deconvolution? So one way that people used to do a lot is so-called phase flipping. So the idea is, instead of, conceptually what we do is we're operating on a CTF that does not reverse polarity. And the way we do it is we take the original image, take its Fourier transform, and we know we take the original micrograph, take its Fourier transform, and then we know what the CTF is. So we know when the CTF is positive and when it's negative. So then we multiply it so that every time the CTF is negative, we flip the sign of the CTF. So we basically take the Fourier transform of the image and multiply it by this 1 minus 1 pattern that looks like the CTF. And when we do that multiplication, then in effect what we're doing is we're operating on it with a CTF that looks like this. It's always positive, and that's the 1D slice through that. And you can see that it's doing a better job of giving you the original object back. There's a lot less dispersion, almost none. It's not perfect. This is it's not picking up the low frequency information quite as well, but it's not too bad. So this is called phase flipping, and this is actually something that you could do at the whole micrograph level if you wanted. And that would allow you to use smaller boxes because you're cutting off less information from dispersion, from delocalization. Now, the other thing you can do is there's something called the Wiener filter, named after Norbert Wiener, who said, well, you can do this deconvolution if you multiply the numerator by the contrast transfer function, but put the contrast transfer function squared in the denominator, and then you put in some kind of regularization constant that keeps the thing blowing up at zeros of the CTF. So you can see that this is kind of like dividing the original image X by the CTF. And you get a better reconstruction of the original image if you go through this process, in effect. You can also and in fact, you can take a noisy image and you can Wiener filter an individual image, and you can kind of see what information you've gotten in a single noisy image using that. But the nice thing is you generalize the Wiener filter so that you're adding together the information from multiple images. So you just add up CTF times the image and divide by, here is the sum of all of the CTF squared. And so now, if we add up more and more images, you can see that we get a better and better, less noisy reconstruction of the original image. Yes. Let's see, adding up. So you could add up multiple phase flipped images, and it's not going to look all that different. It is better with the Wiener filter. That's all I can say. We can also do a fancier Wiener filter, where we replace this constant here that keeps the denominator from going to 0 by letting this constant be 1 divided by the spectral signal to noise ratio. So that means this constant is big when the signal to noise ratio is small, and so this does a proper job of giving you a least squares estimate of what the original object looked like. And so if we go and do this and combine a bunch of images, you can see that once we've combined, in this case, 3,000 images, we can do a really excellent job of restoring the original object. So I want to show you what's happening under the hood with this operation. So this is the Wiener filter. So we're adding together CTF times the image. We're adding those together. We're dividing by CTF squared, and we have this. And all of this is done in the Fourier domain because we're using the fact that CTF times the image, that you operate with the CTF by just multiplying the CTF by something. Okay, so what I want to do is I want to look at what happens in the denominator here, the behavior in the denominator. And so this is what the spectral signal to noise ratio is. I know that a priori, so I can do this. If I don't know this beforehand, then it's trickier. But let's assume that we know the spectral to signal to noise ratio. Then I'm going to compare this term, which is the sum of the CTFs, with this term, which is the so-called regularization term. So here they are sort of plotted, normalized by n, so that we can see the relative sizes. So in blue here is the CTF squared, and in red here is the regularization term. And we can see that the CTF, which is going to pick out the actual data, is larger than the regularization term only at low spatial frequencies, and that's why the result we have is blurry. Okay, but now what I'm going to do is I'm going to add in several terms, several different images. So, so I've done 5 images. Here are 5 different CTF squared, and I used different defocus values for the purpose of filling in zeros of this function. So you'll see that once I add this together, this no longer goes to 0. It goes almost to 0 at that point, but otherwise it's considerably above 0, and that's going to help us because there's no loss of information. And you can see that after we've added several together, then the regularization term relative to the CTF squared term is bigger out to a higher spatial frequency, and that's what we're seeing there. Okay, and then I start adding more and more images with a variety of defocus values, and as that goes bigger and bigger, then the size of the regularization term gets smaller and smaller, and the reconstruction gets better and better. So what's happening under the hood is that we have these 2 terms in the denominator, and as the number of images that I'm combining goes up, then this term gets bigger than that term, and we're getting closer and closer to a perfect deconvolution. Yeah. I'm sorry. How do I determine the? Oh, yeah. Okay, so this is very easy in this case because I just take, I know I have this starting image model which I know, and I just take the square of its Fourier transform, and then average it around and average it radially. I could do this post hoc. I could do this after or during the calculation by looking at my reconstruction and taking its Fourier transform and sort of saying, well, I'll use that at least preliminarily as my SSNR value, and I'll plug it in here. Yeah. Now there's a fancier way, and actually a better way I could get the SSNR, and that is to do a Fourier correlation. So the idea here is I have some good estimate of what the original object was, and I have my reconstruction, and I take the 2 Fourier transforms and I ask how well do these Fourier transforms match. And I do a so-called Fourier ring correlation. So I take a ring in each of those Fourier transforms and I ask what's the correlation coefficient between the Fourier terms in each ring as the ring goes from very low frequencies up to very high frequencies. And that's what I'm plotting here. This is the Fourier ring correlation. It's the correlation coefficient between those 2 rings, and you can see that this reconstruction is valid up to that spatial frequency, whatever it is. Now I can go ahead and start adding more and more terms, and you can see that the correlation gets better and better as we add more terms, and the reconstruction gets better. And finally, when we get up to thousands of images, the FRC looks really good. And it turns out that there's a way to work backwards from the FRC to the SSNR. And in fact, if we had split our data set in two, and we did this twice, one for each of these two data sets, we could then do the FRC between the two halves, and that would give us an idea of how reproducible it was between one half and the other, and actually give us an idea of the resolution of our reconstruction. Yeah. Okay, so this is really cool. We know how to undo the CTF in pretty good fashion using this Wiener filter idea. And so now we can talk about an actual single particle reconstruction program. This is a program called FreeAlign, which was invented by Nico Grigoriev in I think the late 1990s. So first we have to do this thing, we have to first be able to compare pairs of images. We're going to compare an experimental image with a reference. So how are we going to produce a number that shows the quality of matching? So we can look at the squared difference. So what we do is we take the squared difference of each pixel value and add them up, or we can just write it this way. We take the entire image and subtract the reference and get the squared difference. Another way is to do the correlation, which means we multiply pixel-wise the image and the reference. And then there's the correlation coefficient, which is just the correlation that's normalized by the size of the two. Yeah?
What if we have a de novo structure without reference? How do we do this?
Well, we have to somehow have a structure to start with. Yeah, right. So there, in the old days, people would get a de novo structure by forcing the angles to be known values. And so the nicest way to do that is the random conical tilt method, where you tilt the specimen, take pictures, and then you untilt the specimen and take pictures and use the second exposure to determine what the spin was of each particle. And then you take the tilted particle images and you can do a reconstruction, and you know what angle in space each particle was rotated through. Anyway, it was a very clever invention by Rademacher, and that's what people used to do. Now people just throw it in and use the same kind of reconstruction algorithm I'm going to tell you, but just sort of start with a random model. And most of the time it works just great. All right, so we have some kind of reference, and the reference might be a random model, and we're going to compare individual images with it. And so let's see, what am I talking about here first? Okay, before I talk about 3D reconstruction, I'm going to talk about so-called 2D classification. And the basic idea is, suppose I have a bunch of experimental images, and I know that these images are from a population of particles that are just oriented in different ways. And so I want to have the computer classify images that are similar in some fashion. And so the way we do it is we say we have a reference structure. This is one of my class averages. So I operate on it with some kind of rotation and translation, and modify it by the CTF, and say that there's noise added, and that's my model for one of the original images. And so the idea is we compare an experimental image with the reference and compute the correlation coefficient, and then we can estimate the average by doing this Wiener filter thing that I just said, and we can do this for each of the possible classes. Now we can do this also in 3D, and that is the 3D reconstruction process. Okay, let's see, where are we? Okay, so here's what we do. We have some kind of estimated volume. We assume a projection direction, this phi, which is the Euler angles of orientation of this volume in space. We compute a projection, and we're saying, well, a given experimental image is a projection of the original object modified by the CTF with random noise added. And so we saw this. This is just making use of the fact that once we have a projection, we can fill in Fourier space to do a reconstruction. So the problem with doing the reconstruction is that we have to know what are the orientation angles, so that we know where in the 3D Fourier space to insert a plane arising from one of my experimental images. So here's how I imagine an experimental image comes about. I start with my molecule. I compute, I have my molecule, a projection is made of it, and that is modified by the contrast transfer function, and then noise is added, and so this is my model for how a particle image got made. Now, it would be really nice if by looking at a particle image, we can actually tell what was the orientation in space of the original macromolecule, okay? So here's how people do it. You take a particle image and you have your model operated on by the CTF, and you compute the CTF modified projection of the model as you change the angle of orientation. So here we go. We're going through various spin angles and various tilt angles, and I'm plotting here as a heat map the probability of this being a good match. Or let's say this is the square difference between the reference and the individual image. And what is remarkable is that there is a pretty clear peak in the image matching at a particular pair of angles, this much tilt and that much spin, and I can't make the little bar go away, but oops. So the match is really good. It's within a couple degrees, even though the original image looks terrible. This is really amazing to me. And it says that you can, by this kind of projection matching, actually get a pretty good estimate of the orientation of the original object. And so here's a little simulation experiment. So this is an image at the same signal to noise ratio approximately as the original experimental data. And here I added more noise, and here I added more noise. And the question is, can I distinguish, let's say, two different orientations of the original object? So now I'm plotting things as a function of the tilt and the spin angle, and this is the correct orientation, and this is a nearby orientation. And these contours represent the 50% error bound on estimating these angles in a population. So this says that at the original SNR, these angles can be estimated within a couple degrees. And even if the signal to noise ratio gets a lot worse, we can still estimate the angles without too much error. In other words, it's totally amazing. You would not expect it, but you can tell the difference between that and that underlying an experimental image with that much noise. Yeah.
I think you just said it a few minutes ago, just want to confirm. The reference for this is just like random.
Well, so this is doing the best possible case where I said I know a priori what the structure is. But this is kind of like the very process where you have gotten some kind of volume that you think you trust, and you compute all your references from that. Yeah. Yeah.
Which there was like nothing they had beforehand, so
Yeah.
you just start with the blob basically.
Yeah. Well, they actually started with a random conical tilt image, but they did. But nowadays we can get by without that. So now I'm going to talk about Nico Grigoriev's free align program, which was the first single particle program that could get to 3 angstrom to near atomic resolution, and that's because it's the first program that explicitly included the CTF in the calculations. So the basic idea is we vary the projection direction, which I call phi, to find the projection reference, R, which is the volume operated on by a projection operator and multiplied by the CTF. So we have a reference which is a CTF modified projection of the volume. That's what I was just showing you in that animation. And I find the one that maximizes the correlation coefficient between the image and the reference. So I find the best reference, which means I find the best orientation phi. And then the way I compute the volume is it's just another Wiener filter. This is what it looks like. I take the image, I multiply it by the CTF, and in the denominator I have the CTF squared. And then I have this thing transpose of the projection operator. This is the slice insertion operator. This is the thing that inserts the slice into the 3D Fourier transform. And I add this up over all of my experimental images. And so then I'm adding up all of these various slices in Fourier space. And I normalize it by the CTF squared, again, entered in slices. And there's my Wiener coefficient. So this is the free align update. Is we compute references, we find the best angle, this phi sub I, and then we do the slice insertion. So the idea is we start with some kind of preliminary structure, and then you find the projection angles that work the best, and then we use this free align iteration to find the next volume, and you keep doing this until your volume doesn't get any better. Now you can do the same thing with this process called 3D classification, where we just say that I have my individual images, but they came from any of a variety of different underlying macromolecules. And so then I not only determine which angles, but also which volume a given image came from, and then at the same time I can then optimize multiple volumes from one data set. Okay, yeah.
You mentioned that this is an iterative process.
Yeah. Mm-hmm. Yeah.
What if, at the very beginning of this process, you had thought that there was a good match between image and volume, but as you go down the line, those original images aren't as good of a match?
Right. Yeah, so suppose you start off with the wrong volume. then you're going to keep getting a wrong volume if you're not careful. Yeah. So this is a danger. This is especially with the older reconstruction methods, is that it was easy to get caught in a false optimum, and you don't know if you're caught or not unless you try starting various different starting points and seeing if you wind up with the same result. Yeah. Right. So, yeah, so that would not be too bad a place to start, would be to use an AlphaFold model of your macromolecule. Yeah. I mean, much better than just, some kind of random volume. Yeah. Yes?
Following up on that, if your data is very low res, would an AlphaFold, would that bias your data?
Well, anything you pick can bias your result. So at the end, I will tell you about fairly robust ways of working without a starting model, and so you can hold your starting model questions for a little while. Okay, so let's see, how are we doing for time? We're not doing real well. I was telling you various ways of comparing an image with a reference, and now I want to tell you about the statistical method's maximum likelihood. So the image model, again, is the same. The image is referenced with some noise added to it. And what we can do is we can ask, what is the probability that an image came from a reference? The first thing we can do is we can say, let's take 1 pixel. We'll take 1 pixel of the image and compare it with 1 pixel of the reference, and we say that the background noise is Gaussian, and so the value that we get at the pixel could take on a range of values, and the probability that when we get an image here, this is the probability distribution of values, and it's going to be centered on the true value, but it could exist anywhere in that range. So, this is then a normal statistical distribution for each pixel, and we can also do the same thing for every pixel in an image, and so we can do the probability of observing an entire image that comes from reference R, and it looks like this. And it's complicated, and how can you compute that probability? Well, you say, the value that I get in x sub j depends on the width of the finesse of my measurement of the intensity in a pixel, and it depends on the standard deviation of the noise and so on. But I can, as far as doing a comparison, I don't care about the finesse of the measurements. I can just say that it's a Gaussian distribution. Okay, so the probability of observing an image that comes from a reference looks like this. I take every pixel in my image and subtract every pixel in my reference and compute the sum of the squares of all of those, divided by 2 sigma squared, where sigma squared is the variance, and that gives me the probability of getting my particular image from a particular reference. It's a high dimensional Gaussian function. Now, what we'd really like to do is we would like to find the best volume based on our entire data set. So that's what this thing is. This is a probability of given volume based on the entire data set. And what we would like to do is to then change the number in each voxel of a 3D map to make the best volume consistent with my entire data set of images. And so we'd like to optimize this probability. Now, it turns out that from Bayes' theorem of statistics that this probability, which is not obvious how to compute, can be gotten from things that are not so hard to compute. So this probability that we want is equal to this probability, which is probability of getting the particular data set that we did given the underlying volume V. And that is multiplied by two other probabilities. One of them is the probability of that volume instead of some other volume. And this one is the probability of getting this particular data set rather than another. Now, we want to maximize this thing, and we're treating the data as a constant, so we can ignore this term. But this term is kind of interesting. So we know how to compute this, as we'll see in a minute, but what is this? So this is what statisticians call the prior probability. That is, before we do the experiment, this represents what we know about what is a reasonable and what is an unreasonable 3D volume that we're trying to discover. And so the idea is we have some prior information, and then we do our experiment. That is, we take our images with the electron microscope, and we get something called the likelihood out of that. And from the combination of those two, we get the so-called posterior probability, the probability of volumes based on all of this information. And this is how it works. This is the posterior probability. This is the likelihood that comes from the experiment, and this is the prior probability, which is a priori knowledge that we have about volumes. Now, this P of X given V is something that we know how to compute, and it goes by a special name that's called the likelihood. So this is the likelihood of a given volume is this probability, which is probability of data given the volume. Okay, so how do we compute this quantity, the likelihood? Well, what we do is we say, well, we don't know. We're trying to, we have an image. We don't know which projection of the volume we're looking at, but we want to know what's the probability that we got this image from that volume. If we don't know what the orientation was, what we'll do is we will just compute the probability based on all possible orientations, and we'll just integrate over all orientation, and that gives us the likelihood. It's a really cool trick learned from statisticians. So the basic idea is we start off with what we already know, that the probability of an image given the volume and the projection direction is exactly this thing that I was talking about before. It's the image minus the reference based on the projection direction. Okay, and to get the likelihood for the entire data set, all we have to do is we take each image, compute its probability given those things, and because each image is statistically independent, that is, the noise in each image is statistically independent, we can just take the product of all those probabilities. And so that's, so what we do is we integrate over all projection directions, and then we do compute the product over all images, and that gives us the likelihood. This is just a note that this is a really, really tiny number, and so people use the log likelihood. So maximum likelihood estimation is just optimizing that probability that I just told you, and the statisticians tell us that if the size of the data set keeps growing without bounds, but the number of parameters that you're estimating stays fixed, like just the values of each voxel in my volume, then asymptotically you will get the right result, no matter what the situation was, no matter how much noise and so on, you can, if you get the maximum likelihood result for the volume, you can get the right answer. So, but this sounds like a really hard problem because we're to compute this thing, we take each image, we ask what's the probability that it arose from this volume with this projection direction. We compute this for all projection directions and for all images, and we compute this thing, and then we vary v bit by bit to try to maximize this thing. Sounds like a tremendously difficult problem. You know, you have 1 billion voxels to vary. You have thousands of images, and you have thousands of projection directions. So it's a really, really horrible thing. So it turns out that there's a very nice algorithm called the EM algorithm, which does not stand for electron microscopy. It stands for expectation maximization. And to use that algorithm, we have to say we have to compute a function that is the probability of the projection direction itself. So this is so for a given image I and for a given volume V, I want to know what is the probability of the various projection directions. And this is something we know how to compute. This is that Gaussian that I was talking about before. And this is the same thing, except that we're integrating over all phi. So this is just a normalized version of this probability that we already know. So this is how we get the probability of a projection direction. And in that heat map I was showing you as I was rotating all the references and comparing it with the original image, I'm actually just showing you this gamma function. Okay, so it's a probability of a projection direction. So then the EM algorithm, it looks a whole lot like free align, which in turn looks a whole lot like a Wiener filter. So it looks a whole lot like free align, with the only difference being we have this gamma here. And instead of picking the single best projection direction, we integrate over all possible projection directions. So otherwise I hope you can see this is just free align with a fancy extra very expensive integration to be done over all projection directions. Also, this is the Wiener constant, and this T is Sherris's fudge constant in Reliant, that is the that modifies the size of the regularization constant. Yeah.
So part doesn't incorporate this EM algorithm.
It does. It does. I don't think they give you access to this. I don't know. Yeah.
Nothing they give.
They give you nothing. Okay, so anyway, so you're supposed to see that this is beautiful because it's just like free align. Anyway, okay, so so the iteration, if we have if we have a volume which gave rise to a particular gamma function in the nth iteration, then the n plus first iteration volume is given by evaluating this, and this marches in the correct direction towards the maximum of the likelihood, and is much more efficient than, of course, trying to vary every voxel of a volume. And you can also do this for a 3D classification. In that case, you just expand the gamma function so it includes not only the projection direction, but which of the k volumes you're trying to optimize. Okay, and it turns out that this formula, Sherris's formula, works for 2D classification or 3D classification. It's just a matter of of defining what this P and P transpose are. In 3D, it's a projection operator. In 2D, it's an image rotation and shift. Okay, so for example, let's do 2D classification. That is, we have a set of images and we're trying to optimize those, a set of classes which are estimates of the underlying references. And so what we do is we start off, we take some kind of starting reference, which is maybe one image, and we take a set of different images and we ask, what is the probability, what does the gamma function look like? And the gamma function has translations and rotations in it, and it also tells us which class is best matched by a given individual image. And so, as we start the first iteration, we start with this kind of with these random starting models, and we see that if we give this translation and those rotations, then turns out that it matches this class and that class the best. So this is the first iteration, and as we go through various iterations, we see that the assignment of classes gets better with time, and the assignment of angles and positions gets better. And so by the time you get to the last iteration, the classes are pretty well defined, all except in this instance. The angles are pretty well defined, except in this instance. And as we go through these cycles, we're also tuning up our estimates of the classes. And so you can see here the classes have high resolution details in them. Yeah?
How do you determine the number of classes?
This is something that the user gives. And this is a problem. If you really had to know how many different classes you had, it's rather tricky to determine that after the fact. But what we do is we say, I have this data set of 100,000 particle images, and I want to see roughly what views of the particle I've got, and so maybe I will sort them into 100 classes or 30 classes, knowing that the smaller the class numbers, the more there's going to be blurring from combining particles with slightly different views. Yeah. Now you can do the same thing in 3D reconstruction. This is a primitive 3D reconstruction. So we have particle images, we have a projection of the 3D volume, and here are the parameters of the gamma function, translation, in-plane rotation, and tilt and spin. And as we iterate, these distributions become sharper and sharper, and we get better and better estimates of the 3D volume as we go through these EM iterations. Now the problem is that as I've described to you, the calculation is really expensive. You have to try a whole lot of different orientations, and the 3D reconstruction, the slice insertion is not so bad, but finding the orientations is really expensive. Years of CPU years, even for an only 128 by 128 pixel box and 100,000 particles. But there are much more efficient programs, and I want to give you an idea of how the efficiency comes about. Basically, let's try. We just want to know what the in-plane orientation of a particle is in a particle data set. So what we do is we compute the probability of the particle orientation based on the data, and here there's a maximum, and the maximum happens to be at the right value, but here the maximum does not occur at the right value because the signal to noise ratio is so terrible. Here it is at the right value again. Here's the wrong value again. So how are we going to do it? We can't just pick the peak value. We're going to have to do this horrible integration over all possible orientations. So the idea is we actually don't have to integrate over all possible orientations. We can figure out a way to just search in the most important regions of the parameter. And so there's this procedure called branch and bound. What we do is we search the orientations at low resolution, which is much cheaper, and then we ask how high could the actual value be if the low resolution value is that, and then we just take all of the regions where the upper bound is above some threshold, and we just do the integration over this small part of the domain, and that speeds things up. In this case, it's probably a speed up of tenfold. So this is how CryoSpark does it. It does this in the most elegant way. This is what you would get if we look at tilt and spin and make a heat map where this is the correct pose, that is the correct spin and tilt of the 3D object. So the way CryoSpark does is it evaluates this entire map, but at low resolution, so it's relatively cheap, and then they prune everything that does not promise to give a high upper bound on that probability, and then through a pruning step they reduce the domain over which to search, and then on the second iteration they can then prune the vicinity of the maximum. And so here in 3 steps in this example, they can get a very good high resolution orientation by bootstrapping off of low resolution orientations. Now, the other thing that CryoSpark introduced is a way to get out of local minima or local maxima. So the EM algorithm, as I showed you, so if you start with some kind of ugly looking initial model and you just go and iterate the EM algorithm, you get some kind of nonsense structure. If we started with something with a good initialization, then we would get to the correct high resolution structure. So what CryoSpark does is it introduces randomness into the reconstruction process by stochastic sampling. Basically, instead of using all of the images for each step of the EM algorithm, they start with a random subset of images to make the first step. And they also compute a gradient which allows them to move to the maximum quicker. But anyway, so you use one random subset for the first step, that is to get it to here. You use another random subset to take the second step, which gets to here. You take a third random subset and it makes a jump. So this is introducing randomness into the optimization process, which fortunately usually gets you out of the false maximum and takes you up to the correct value. So this is the SGD, or stochastic gradient descent. So anyway, so that's how Relion works. Relion does this maximum likelihood EM algorithm, and CryoSpark does it, and CryoSpark does it in this clever process, and now Relion has some speed up along the same way. There was a question.
The randomness here, that
So basically, the basic problem is if you just follow the EM algorithm, it's only guaranteed to bring you to a local maximum. And so you want to introduce some kind of randomness so that you will get taken out of the local maximum and get to the global maximum. And the general idea is, well, let's do it by introducing some randomness. And besides, let's introduce the randomness in a very inexpensive way by just operating on subsets of the data. So it's a clever way to do it. Yeah.
So for the projection direction computation,
Mm-hmm.
how do you know or how does one consider how many projection directions you can try and fit things to? I guess because it would probably be related to the Nyquist if you try and get all of them. But
Right. Yeah, so it's related to the Nyquist. And the way it's done is this: you say your particle is some size, or let's say has a certain radius, and then the smallest angle you need to test is an angle that will just take you one voxel at that radius, up or down, and so that sets the angular fineness that you have to take.
that sounds computationally expensive.
Yeah, that's right.
That they get around that, or do they actually, or do these programs actually compute the projection?
Well, so that's why the first pass is at low resolution. You know, suppose you're working at 10 times or 8 times lower resolution, then you can use angles that are 8 times bigger, and you have 3 angles to deal with. So that's 8 to the third faster computations, and so that's why you do a coarse you do a coarse angular distribution, and then you refine that.
And then at the final iterations, does it consider all of them, or does it consider the resolution that you're operating at and take that into account?
So it then uses these fine steps, but fine steps only in the region where the coarse analysis said the best is supposed to be near this. Yeah. Yep. Okay. So anyway, so I like to say this, that it's amazing that this works, and it's essentially magical. Okay. So.